Hi, my name is Reed Bailey, and this is a video on analysis of variance and why it's important and what its use is. This is another video in the Intuitive Statistics series where our real focus is on when to use certain statistical tests. The focus is not on the formulas and proofs of these statistical tests that we assume you've already seen in a traditional statistics course. Up to this point, learned about different kinds of t-tests, one sample t-test, independent samples t-test, paired samples t-test, and in this video we're going to be pushing into areas where these tests struggle to handle the questions that we're trying to answer. In this case, our example question deals with an opera company that is trying to raise funds. So instead of a bake sale, which would be a great idea, they're going to try calling up different donors or sending different donors letters or emailing different donors. One of these three approaches is going to be tried on each of 24 sponsors to determine which of these different approaches leads to more money being donated. You might imagine that the data could look something like this, where on the x-axis is the amount of dollars being donated, and here are three nominal distributions showing that for approach 1, you can see the mean value. It's the blue distribution with the mean value y bar 1. Approach 2 is looks like it has the highest mean value in the red distribution, and approach 3 has the lowest mean value. It's the green distribution. So given the data and for these three different approaches, and only considering the approaches that you already know for looking at statistical difference, how could you use these approaches you already know to determine if these three approaches were statistically significantly different? Pause, think about that, and when you're ready to move forward, come back and start the video. All right, welcome back. Had a minute to think about this. A lot of people will come up with the following answer. Well, why not just run a bunch of t-tests? You could run a t-test between approach 1 and approach 2, another t-test between approach 1 and approach 3, and a third t-test between approach 2 and approach 3. Seems perfectly reasonable given what you know up to this point. And the problem with this approach and why you don't want to do it is something called alpha inflation. And remember, alpha is the term we use for type 1 error, and essentially it adds up each time you run another t-test. Now, I want to get into why that happens just so you have a little better feel and you don't have to just trust me that alpha inflation is a problem when you run multiple t-tests. Now, in order to talk about alpha inflation, we need to talk a little bit about probability. So we'll start with this question that all of you will be able to answer. What's the probability of rolling a 6 on a die? Well, there are 6 sides, so it's 1 out of 6, or about 16.7% chance of rolling a 6. Let's say you roll the die twice. Now, what's the probability of getting at least 1 6 after you roll the die twice? You might want to pause the video here and think about that for a second. All right, maybe you've had a chance to think about that, hopefully. A common way to think about this in a probability class is to reverse the question. Instead of saying, what's the probability of getting at least 1 6, is what is the probability of not rolling any 6s? Because we know each time we roll the die, there's a 5 out of 6 chance that we're not going to roll any 6s. So if we roll it twice in a row, that's just going to be 5 out of 6 times 5 out of 6, which net's going to be 25/36. So if there's a 25/36 chance of not rolling any 6s, now we can go back and answer our question about what's the probability of getting at least 1 6. It's just 1 minus that, or about 30.6%, 11/36. Well, we could extend that out to say, what's the probability of rolling at least 1/6 in n rolls? And now the equation would look like this: 1 minus, and then in parentheses, 1 minus 1/6 raised to the n. And if we were to carry this out, you could see that, well, if n equaled 1, that'd just be 1 minus 5/6, or our answer would be 1/6. If n equals 2, that's the answer that we just got: 1 minus 5/6 squared. N equals 3, n equals 4. And you see what happens, very intuitive, is that the more rolls that you make, the greater the chance is that you're going to get at least 1/6 in one of those rolls. And at 4 rolls, you have over 50% chance of seeing at least 1/6 after 4 rolls. So now, how does this relate back to alpha inflation? So we've been talking about the probability of rolling at least 1/6, and here's our equation that we've been using for it. Well, that's been an analogy for us to the probability of a type 1 error, or we would say probability of alpha, because that's the term we use for type 1 error. And this is a really critical analogy. It's that every time we run a statistical test, it's analogous to rolling a die. It's not a perfect analogy, but it's close enough for you to understand what alpha inflation is. Every time you run a test, it's like rolling a die. And so our equation would shift over to this, where alpha star is like our effective alpha, our effective type 1 error, would equal 1 minus, and then 1 minus alpha raised to the n. So for alpha equals 0.05, which is normally one that's used or one that's frequently used, if we just run one statistical test on a certain dependent variable on a certain set of data, our effective alpha is 5%. If we ran 2 tests, it would be 9.75%. And remember back on our example for the opera fundraising, we would have to run 3 t-tests to test all combinations, pairwise combinations of the donation strategies that were tried. If we had run 3 of those tests, our effective alpha, our effective chance of type 1 error would be over 14%, even if we were just using an alpha of 0.05 in each individual statistical test. That's what alpha inflation is. All right, with that being alpha inflation, hopefully you can see the problem with running multiple t-tests, that the true alpha isn't the alpha that you're looking at. So just because you were to receive, let's say, a p-value of less than 0.05, if you ran multiple tests, that really doesn't mean that your type 1 error is as low as the p-values are showing. So here we're back to our example. What do we do? Alpha inflation prevents us from using multiple t-tests in a simple way. Well, one of the things we can do is create a lot of complicated statistical methods for adjusting the alpha to take into account this fact of alpha inflating in a way like what we just showed. And the numbers we just showed were like a maximum value for the, let's say, the alpha inflation that you could see. Well, okay, we're not going to do that. We'll leave that to other folks, Tukey and his statistician friends. What we're going to do is use ANOVA, which uses a fundamentally different approach to detect differences between means than t-tests. And that fundamentally different approach will be the focus of the next video. Well, all right, we've learned today that when you have more than 2 levels for your independent variable, t-tests really start breaking down and alpha inflation becomes an issue, so analysis of variance becomes a good test to use. We'll talk more about key assumptions in a different video. So when would you use ANOVA for our examples here from the Panama Canal? One possibility is, which month of the year has the most transit in terms of ship tonnage through the canal? Choice B is, did tugboat captains who participated in a training program reduce the average transit time of their ships compared to before the program? Choice C is the average salinity of water in Lake Gatun lower than 1.100 part per thousand? And then choice D, are ships originating in China or Japan carrying on average more valuable cargo? Well, before we get to an answer to this question, let's review what we learned today. The big topic here was why we use ANOVA in the first place. It's because when we have more than 2 levels for our independent variable, alpha inflation becomes a problem with t-tests. And so using analysis of variance gets us around that problem. Returning to our questions, in which of these 4 cases would you use analysis of variance? Well, if you answered A, you're correct. Which month of the year has the most transit in terms of the ship tonnage through the canal? The dependent variable, ship tonnage, is a ratio variable, so analysis of variance is appropriate. Month of the year is the independent variable, and it has 12 levels to it, which is clearly more than 2, so we wouldn't want to use a t-test. Hence, analysis of variance would be the test you would use to answer the question, which month of the year has the most transit in terms of ship tonnage through the canal?